You are looking at the terminal of a Dorado workstation running the Cedar programming environment. On screen is a control panel for Gargoyle 3D, an interactive three-dimensional drawing tool. The square shape moving through the drawing area is a hardware cursor controlled by a mouse. This two-dimensional cursor can be used to control the position and orientation of a three-dimensional software cursor called the skitter. When the cursor passes over the cube, gravity snaps the skitter to the nearest cube face and orients its z-axis to be perpendicular to the surface. When the cursor passes near a line, the skitter snaps to the line's nearest point and the x-axis of the skitter becomes parallel to the line at that point. When no objects appear near the cursor, the skitter snaps to an invisible plane parallel to the screen. Gargoyle 3D provides 3 gravity modes, which determine what part of an object the skitter will snap to. Face's preferred gravity snaps the skitter to the nearest surface. Line's preferred gravity snaps the skitter to the edge that appears nearest to the cursor or to the nearest face if no edges are near. Both visible and hidden edges are gravity active. Finally, Point's preferred gravity snaps the skitter to the nearest vertex to the cursor, the nearest point of intersection to the cursor, or to the nearest edge or face if no such points are near. Gravity can be used while new lines are added to the scene. Here, Point's preferred gravity is used to add a line from one cube to another and to construct the major diagonal of a cube. A special object called the anchor can be placed by typing a keyboard command. The anchor takes both its position and orientation from the skitter. I will delete the block that I used to place the anchor. Note that the anchor attracts the skitter. In order to make precise shapes, I can activate a set of alignment objects, lines, planes, and spheres. Here, I activate alignment lines with slope of 0 degrees and azimuth of 10 degrees, and alignment spheres of radius 4 inches. A resulting line and sphere are constructed, centered on the anchor. The skitter can be snapped to the surface of the sphere, to the alignment line, or to their intersection points. I add a line segment from an intersection point to the anchor. When I make the right hand endpoint hot, it triggers alignment objects just as the anchor did. A new alignment line and sphere appear. The system automatically computes and draws the circle of intersection of the two spheres. I add a line that ends on that intersection circle. Adding one more line, I complete an equilateral triangle in 3 dimensions. To construct a tetrahedron, I make one more point hot. A third alignment sphere appears. I add a line to the point of intersection of the 3 spheres, deactivate the alignment spheres, and complete the tetrahedron. I can activate a set of alignment planes by specifying the slope and azimuth of their facing direction. Here I activate planes of slope 90 degrees and azimuth 0 degrees. An alignment plane is drawn as the projection of a small square. As additional planes are activated, their lines of intersection are automatically drawn. When the skitter snaps to a plane, the square representing that plane darkens. When the skitter snaps to a line of intersection, both squares representing the 2 intersecting planes darken. I can use these 3 mutually perpendicular planes along with an alignment sphere to construct an octahedron. The circles of intersection of the sphere with the 3 planes are automatically drawn. Those 6 points where the 2 planes meet the sphere are the vertices of a regular octahedron. I add lines between adjacent pairs of intersection points, deactivate the alignment objects, and complete the construction. The ability to precisely place the skitter can be used to implement a set of precise translation, rotation, and scaling operations. I will use these operations to attach a tetrahedron to one face of an octahedron. I place the skitter on a tetrahedron vertex and begin a translation operations. The skitter and tetrahedron move as a unit. Because the scene objects continue to be gravity active, I can snap the skitter to a vertex of the octahedron. I drop the anchor to be used as a center of rotation and place the skitter on the other end of this tetrahedron edge. During the basic rotation operation, The line from anchor to skitter remains collinear with this edge, so when I snap the skitter to the octahedron, the two polyhedra share an edge. Objects can also be rotated about the x-axis of the anchor. During this rotation, the tetrahedron's face remains coplanar with the skitter. When the rotation is finished, the tetrahedron rests on a face of the octahedron. Again, I place the skitter on a tetrahedron vertex. During the scaling operation, the distance of the skitter from the anchor determines the amount by which objects are scaled. Snapping the skitter to the octahedron vertex makes all of the edges congruent. Snapdragging can be used to form precise relationships between objects that are far apart. For instance, to make the arrow point at the center of the sphere, I place the skitter at the tip of the arrow and rotate the arrow about the midpoint of its tail end until the skitter snaps to the center of the sphere. To move the block on the right to be at the same altitude as the block on the left, I make one vertex of the left-hand block hot and activate horizontal alignment planes. I select the right-hand block and translate it onto the alignment plane. If I want the blocks to have collinear edges, I can use an alignment line instead. To rotate a cube about one of the main axes of the reference coordinate system, 3 perpendicular alignment planes and an alignment sphere can be used. By moving the skitter along an intersection circle, I can rotate the cube around x, y, or z axes. If the skitter begins and ends at an intersection point, the cube rotates by a multiple of 90 degrees. Finally, if I deactivate the alignment planes, I can apply a free-form rotation. It is useful to be able to transform parts of objects as well as entire objects. For instance, if I select the right-hand cube and translate it up, I leave behind the 4 lines that formerly made a bridge. However, if I select the ends of the 4 lines as well as the cube, the bridge stays connected during translation. Gargoyle 3D allows the user to select parts of objects by pointing at them. Pointing can be ambiguous. For example, I am now selecting a vertex, but to which of the 3 cubes does it belong? The system allows me to cycle through the vertices that were behind the cursor when the selection was made, selecting them in turn. As each vertex is selected, the unselected vertices of its cube are highlighted with white squares to disambiguate the selection. Selecting faces may also require cycling. Right now, I may be pointing at one of 4 faces. By default, the system assumes that the nearer face is intended, but I can cycle through the faces behind the cursor to select the left face of the right block, the right face of the left block, or the back face of the left block. Even with perspective, it can be hard to tell how deep in the scene an alignment line is and to pinpoint the vertex that triggers it. When the skitter snaps to an alignment line, Gargoyle 3D draws a starburst to highlight the vertices that trigger that line. Here, we see that this alignment line is triggered by vertices at the top of this wall of blocks, while this alignment line is triggered by the second level. In addition, when I snap to an intersection point, vertices that trigger either of the intersecting lines are highlighted. For instance, 2 starbursts appear when I snap to this intersection point or to this one. A group of objects can be selected at once by stretching a block through the scene. All objects that are contained in the block are selected. This can be used to rotate one face of a Rubik's Cube. In summary, gravity can be used to snap the skitter to faces, edges, and vertices in the scene. Alignment objects provide additional surfaces, curves, and points to which the skitter can be snapped. Transformations, such as translation, rotation, and scaling, All follow the skitter.